So in this video, we're going to introduce the concepts of quantization through and connections to the Bohr model of hydrogen. And what we're going to see is that ultimately the modern understanding of atomic structure, of what atoms actually look like in terms of protons and electrons and energy, a lot of this understanding comes from experiments in physics and um, trying to understand the nature of light. The nature of light. Okay? So light is one form of electromagnetic radiation. Electromagnetic radiation. And well, when we think of light, we think of the stuff that we can see. You know, we think of with our eyes being able to see different colors and whatnot. What that actually represents, the light that we can see actually only represents a small percentage of light in the electromagnetic spectrum. So if you look at this box here, this shows the electromagnetic spectrum for a bunch of different what are called wavelengths of light, as we'll see. So these numbers here represent wavelengths. And don't worry about noting this diagram or anything, but it's just interesting to recognize that visible light, okay, what we can see with our eyes only falls in this range. There's a lot of other different wavelengths of electromagnetic radiation that we can't see with our eyes. So for example, ultraviolet is a shorter wavelength, and we can't see that with our eyes, but it causes damage to our skin, and we have to protect it with sunscreen and whatnot. X-rays and gamma rays represent even shorter wavelengths of light, again, that we can't see with our eyes, but we know exist through experiment. Infrared, otherwise known as IR, microwaves, radio waves, these represent longer wavelengths of light. Again, you can't see a radio wave, our eyes are not adapted to be able to do that, but we know that they exist through experiments and all this other technology that have harnessed the power of this. So through experiments and trying to play around with and observe different aspects of electromagnetic radiation, a lot of our understanding of atomic structure has developed from that. So there's three main terms that we're going to focus on: wavelength, frequency, and quanta through the course of this video. So the first thing to know about light is that light behaves as a wave. Light is a wave. And so we can represent it if we were to draw a wave of light, okay? A wave is just a repeating process over and over and over again. And there's a few terms that we need to know. The distance from one peak to another peak, or from one what's called trough to another trough, this distance in which it repeats, this distance can be measured in meters and is what is called the wavelength. Okay. So like we said back here, visible light has a wavelength of about 10 to the negative 6th meters. X-rays have wavelengths of 10 to the negative 9th, radio waves 10 to the 3rd. So they really vary in distance. The units, we usually abbreviate wavelength with the Greek letter lambda that looks like this. Okay, so this is pronounced lambda. And we can use that to measure any wavelength of light. Okay. Another relationship that we need to know is something that is called the frequency. Okay. And the frequency is usually abbreviated with the Greek letter nu, which kind of looks like a little V, or sometimes just with an F, like this, for frequency. What frequency is the number of cycles per second. So the units for frequency are usually 1 over seconds, which are often sometimes called hertz, which you guys are might be familiar with. Okay, so these are the units for frequency. Meters are the units for wavelength, and both of those can be used to describe different waves. So for example, just to give you a visual, let's draw one wavelength, or one wave right here. Okay. Boom. Its wavelength would be this distance, and let's say this takes 1 second to get here. We can see that there's about 1, 2, 3.5 cycles per second with this wave. If we add another wave that looked like this, we can see that it has a much longer wavelength, and that its frequency is much less because it's only about 1.5 cycles per second instead of 3.5. So we're seeing a relationship between frequency and wavelength, which are inversely related. Okay? So we can quantify that relationship by saying that wavelength is inversely related to frequency. But there is a constant that relates them to, and that is what we abbreviate with the letter c. C is the speed of light. So light travels at about 3.00 times 10 to the 8th meters per second. Really, really fast. Okay? But what that means is when you turn on a light switch, the light that comes out from the light bulb to your eyes, it doesn't have it instantaneously. It actually takes a small amount of time for that to occur. And depending on the wavelength, the frequency of that might change. So the relationship that we need to know, since they're inverted, is that the frequency, which we'll abbreviate with nu, times the wavelength is equal to the speed of light for every every wave on the electromagnetic spectrum. Okay, so again, this is frequency and this is wavelength. So you always know this. This is a constant. It's 3.8 times 10 to the 8th, excuse me, 3.0 times 10 to the 8th meters per second. And these two things are indirectly related. Okay. Now, a lot of knowledge that we've gained about light uses the idea that it is behaves as a wave. However, there's three kind of experiments that can't be explained by the wave nature of light. Okay? And those three experiments are what are called, or observations, are black body radiation, which has to do with the amount of heat or light that's emitted from really hot objects. The photoelectric effect, which has to do with electrons being released from certain metals, and something called emission spectra. Both of these are pretty cool concepts, but we're only going to focus on emission spectra because that really connects to the atomic structure and structure of atoms. What you can see here are examples of emission spectra. Emission just means released, and spectra just kind of means light. So we're talking about light that gets released from different elements, hydrogen, sodium, helium, neon, mercury, and we're going to explore why this actually happens and why this exists. Okay? But why this didn't work with the wave nature of light, remember, is because if light, we think of light as just being this continuous spectrum. You might remember the letters of the alphabet, Roy G. Biv. Light, we can have all these different colors and a gradient from violet to red. There's all these unlimited possibilities. However, different elements don't show that. And so what was tested was when certain elements, and all elements actually, but hydrogen was a gas that was used first, when it is electrified, when a current runs through it, and that light is passed through a prism, we don't see all of the wavelengths of light that we would expect. For example, when hydrogen is a current runs through it, we only see 1, 2, 3, 4 wavelengths of light in the visible spectrum. Only these 4 exist, not all of them. And that doesn't really make any sense because we would expect to be able to see all wavelengths of light if light behaves as a wave, because we can see all of it. But this is telling us that, this light seems to be behaving as discrete, specific wavelengths only, not every possible one. And so that was a challenging idea. And so what that led is to the idea of quantization, which was detailed by a guy named Max Planck in 1900, where he hypothesized that the reason that this happens, where light only exists in these specific wavelengths, is that energy only exists in specific wavelengths or in specific discrete amounts. And he called those amounts quanta. So quanta are specific amounts of energy. So to give you an analogy for this, if light was not quantized, if all possibilities of light existed, and you were trying to go up, up to this point and you were walking, we would just have a ramp, okay? This is just an analogy. You could go anywhere on this ramp. You could go here, 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 here. There's an infinite number of possibilities of where you could be on this ramp. Just like we would expect there to be an infinite number of possibilities of light. But that's not what we're observing. What we're observing instead is there's only specific levels or amounts where light can be. So instead of this being really like a ramp, it's more like a staircase. Okay? Where energy doesn't exist in an infinite amount of spots. It only exists actually in certain discrete steps. So energy can only be where these steps are. Energy can't be in between. There's only these different levels of where energy can be. And those levels, those specific amounts, are called quanta. Quanta. And so this led through some math work for Planck to come up with an equation that says the energy of light, the energy of electromagnetic radiation, is equal to a constant times the frequency of that electromagnetic radiation. So again, this is the frequency, and this is what's called Planck's constant. And Planck's constant has a value of 6.626 times 10 to the negative 34th joules seconds. So if we think about this, this is saying that depending on the frequency of light, there's only a certain amount that if we change the frequency, the amount of energy can go up by. Now that amount is a really small amount, 10 to the negative 34th. That's a very, very, very small number. So small that it might almost seem like that light can be continuous, but it can't be. So these steps kind of exist in differences in energy of about Planck's constant, 6.626 times 10 to the negative 34th. Okay? So how does that apply back to this? Well, what that is saying is that when we pass a current through this gas of hydrogen, it has some energy. And that energy that gets released in the form of electromagnetic radiation only gets released in specific steps. And those specific steps for hydrogen, based on its frequency, correspond to wavelengths of 410 nm. So nm is a nanometer, which is 10 to the negative 9th meters, 434 nanometers, 486.1, and you can't see it underneath my face here, but 656.2. Okay? And all those values correspond to different colors in the visible spectrum, which is pretty cool. Now for different elements give off different frequencies of light, and because we know that energy is equal to Planck's constant times the frequency, that means that the amount of energy given off is going to be different too. So for hydrogen, we see these specific bands. For helium, we see these bands. Neon, sodium, mercury. And so this kind of allows us to predict what colors we would expect to see from different elements, which is really pretty fascinating. And we'll derive one more equation together in a little bit. But how does this connect to atoms? How does this connect to the structure of an atom? Well, we've learned this diagram before, where that in the center of all atoms is the nucleus, and then around the nucleus are rings where electrons orbit, kind of like planets around the sun. As we'll see next, that's not quite a fully accurate picture. But for the purposes of hydrogen, what Niels Bohr determined was this makes sense mathematically in relation to what we know about emission spectra. What he said, okay, is that these rings right here, these differences are kind of like differences in energy, change in energy. And that is kind of like the energy that's associated with that equation we just came up with, Planck's constant, saying that it's quantized. So think of these rings kind of like steps, where the electrons can't exist, on a ramp. They can't exist anywhere in an atom. They can't exist in this area, for example. They can only exist at this level, or this level, or this level, like at this stair, or this stair, which have different amounts of energy. Now, to break it down even further, we know that the nucleus is positively charged and electrons are negative. The closer these two things are together, the more attraction that there is, the greater amount of energy. The further they are, so like this distance here versus this distance here, since they're further apart, there's less attraction. There's a difference in the amount of energy. And what Bohr kind of hypothesized was that if an electron, let's say this electron, this atom gets hit with some energy and it moves up to a further away energy level when it absorbs some energy, then when it falls back down to that ring, it releases energy. So when electrons move down rings, they release energy. And guess what? That amount of energy is equal to Planck's constant times the frequency of the light that is emitted. And so if we combine that back with our earlier equation, that the speed of light is equal to the wavelength times the frequency, we can combine these two equations together. So in this one, for example, I'm going to solve for frequency. Okay, so I'm going to divide by lambda on both sides. I'm going to have frequency equals the speed of light over lambda. I'm going to substitute that in here. And I'm going to rewrite that energy is equal to Planck's constant times the speed of light divided by the wavelength of light. So what this is showing us, which is really pretty cool, the amount of energy released by an electron tells us the wavelength of light that will be emitted. So from that, Bohr could hypothesize, okay, if the amount of energy released is this, I predict we should see a wavelength of this many nanometers. And guess what? All his predictions mathematically corresponded to what we saw experimentally. So this idea worked for the Bohr model of the atom. Whew, that's a lot of concepts, a lot of big ideas. The main thing to take away is that energy is not continuous. Energy is quantized. It only exists in discrete steps, which we know in terms of atoms has to do with discrete rings where electrons can exist. Okay? The other things to know are based on this equation, right here in blue. Wavelength and frequency are indirectly related. So if you have a longer wavelength, that means you're going to have a lower frequency. Okay? In addition, based on this equation, we can see that energy and wavelength are indirectly related. So if you have a shorter wavelength, that means you're going to have a higher energy. And just to connect that to the real world to wrap up this video, if we go all the way back to our first page, we said if we have a shorter wavelength, that equals increase in energy. Well, what light in the electromagnetic spectrum is dangerous to us? Ultraviolet causes skin damage. X-rays can cause cancer. Gamma rays are high energy. And what do we notice here? They have smaller wavelengths. As you get a smaller wavelength, they become more energetic. They have more energy, which can cause more damage. So this is going to give us the foundation for atomic structure, and we'll move into more details in the next video.